Hello, am I audible?
And I'm just you're audible.
What? It was not clear. I'm audible to you, right?
You're audible.
Okay. Okay, thanks. Okay, we'll start the lecture. Let others join in the meantime. Today is the Monday session, so we will revisit all the contents this week holds. This week starts with frequency responses. So far, we have been discussing about time responses. Now we are going to go into the frequency response specifications and their control designs. Okay, right. In time responses, what we have done, we have done PID controllers and we have done time response analysis where we will analyze the how the time response or the plots shows. For example, if this is a plot, we have studied what is the peak overshoot, what is the settling time, rise time, all the time based specifications we have seen in the time responses analysis. And using this, and if the overshoot is like this and I want the overshoot to make it like this, I have designed a PI or PID controller according to the requirement. So now we are going to do the same thing exactly, but in another how to say, another domain, frequency domain. Instead of time domain, we are going to work in the frequency domain. What is the major difference between this time domain and frequency domain is that, let us split this into two different things: time domain and frequency domain. In time domain, it is easy to analyze the system behavior with respect to time. In frequency domain, the major advantage is that it is easy to design controllers to make the system behave in our required way. Here also controller design is okay, but when I have PID controller, if you remember, the KP, KI, and KD are being arbitrarily tuned. In sometimes for some systems, we don't know what to tune or how to tune this PI, PID controllers. We require some external method like Ziegler-Nicholas plot to make this tuning. But in frequency domain, it will be easy to analyze the system and also to design a suitable controller so that we can make the system work according to our requirement. This is the one big advantage when you go to the frequency domain. And the representation of the system is very easy when compared to time domain. In frequency domain, representing a system and doing an operation, for example, in frequency domain, everything will be a multiplication, not like convolution or any other things. So when in time domain we do convolution, in frequency domain we just do multiplication. So it will be easy to compute, and also the resources required to do using any computer or any PCs, it will be easy. Instead of spending so much resources on convolution, I can just straight away do a multiplication and get things out of. So these are several advantages of using a frequency domain. So let's see how we can analyze a system in frequency domain, right? Okay. First thing is frequency response is a steady state response of a system when the input is sinusoid. So we used in time domain, we have been studying different inputs like step, impulse. These are like real signals that can mimic some real input signals. For example, impulse mimics a lightning, step mimics the switching on a switchboard, kind of ramp mimics a accelerator that goes from 0 to 100 in a second. So these kind of signals we have seen in time domain. So in frequency domain, we are going to, or particularly what if someone asks what is frequency response, we'll say it's a steady state response after some time where it is reaches. That is a steady state response of the system when the input applied is a sinusoidal signal. So if you feed your system a sine wave, wait until it comes to a steady state point and observe the system's output. That gives you a frequency response in real time application. Okay. Why it is useful? Any idea you have? Why frequency response is useful based on the things I have said before? You don't need any model of the system. Important point is that you don't need any model of the system. If you have a black box system, black box means you don't have much idea or knowledge about the system. Some system you have and you are giving one input and you are getting some output out of it, and based on this input and output and some very few knowledge of the system, for example, if the system is linear or non-linear, based on the output itself we can say if the system is linear or non-linear. So based on this few knowledge of the system and the input and output, we will be able to design a controller for the system. So we don't need any exact model of a system. In this way, frequency response would be useful. And it helps identify system parameters and uh, in if you see these are like basic control course. If you go to robust control or optimal control, this will be very much helpful. It helps you design a controller that is very accurate compared to the basic controllers. The idea behind this is, if we, I will explain it here. We take a LTI system that is a linear time varying, time invariant system. Linear time invariant system. Take a linear time invariant system considering R of t is equal to A into sine omega t. Some sine input I am using with the magnitude A and frequency omega. And I would expect an output like this d sine omega t plus. This we all know, right? If we give an input of a sinusoidal signal A sine omega t to an LTI system, we will get an output sine where this frequency would be changed by phi and magnitude would be b. So where b will be a into j of g omega, where g is your transfer function at j omega frequencies, and phi, your phase angle change, would be angle of g of j omega. So this is the knowledge of the system. This LTI system is this g of j omega. So this change will be directly related to the system's transfer function at g of j omega, right? In Laplace domain, we used to call g of s. Here we are not considering the real axis. We just, where s is sigma plus j omega, right? Here in frequency response analysis, we just consider g of j omega, considering sigma equal to 0, right? So this turns the Laplace domain into the frequency domain. Now we are considering an input. Before going through this, anybody watch the lectures? If you have any particular doubts, you can ask me. Otherwise, I don't know in which particular part you would need help. we will be telling everything, and someone will feel that's too much. Like you have already seen the lecture, someone will feel completely blank. So based on your feedback, we will be able to do it better. So you can tell me whether you have watched the lectures, you have some knowledge about the things, and you have any particular questions. So in that case, we can discuss that straight. Or you want me to start from the basics for this frequency response?
I have watched the first lecture alone.
Okay. Mhm. Anybody else wants to tell? Or you want me to explain like just about everything?
Actually, we can skip the first lecture and do it from second, or whichever part you think is important, we can.
Okay. Right. Okay. For those who didn't watch first lecture, I'll give a gist and then we can move towards the main part. The first lecture explains about the introduction about the techniques we are going to see later during the lecture 3-4. That is, we usually focus on these methods, that is Nyquist plot and Bode plots. These are two different frequency based methods. So if you want to relate this with the known concept, is that's a root locus. This we did for the time response or time based domains. We are going to do for the frequency domain. So more or less everything is going to do a same purpose. What we did in a root locus is that we have an open loop or a loops transfer function. Have something s plus v by s plus b. So from this loop transfer function, I am going to see how my root locus varies when I change the gain k from 0 to infinity. So whenever I want, for example, if I put k equal to 1, I should be able to get where the poles or closed loop poles will be when I put k equal to 1 from the root locus itself. I don't want to calculate the closed loop transfer function explicitly, because calculating closed loop transfer function for second order system would be good, but for higher order systems it will be very difficult and computationally it is very time consuming. So with the Nyquist plot, I will be able to tell where my system's pole location, closed loop pole location will be from only the open loop transfer function. This is the very what to say advantage of the root locus method we studied for the time domain uh, control systems or systems, whatever it is. Similarly, we want some tools in frequency domain systems also, so where we can use those tools to analyze the system that has been represented in frequency domain. That is this Nyquist or polar, both are same, and the Bode plot. So these are the two frequency domain analysis tools where it has similar but little different purposes that we are going to see in lecture 2 to 4. Right. Before that, I want you to know basics of this frequency domain systems. For example, if we take a open loop system, considering C of s is equal to R of s into G of s, G of s or into R of s, whatever it is, I'm going to consider R of s as a um, sinusoidal signal where I consider a square plus omega square, and I'm going to, if it is like that, I'm going to split the output response into two parts. That is a transient part, as we did in time domain specifications, right? Steady state part. Here, this is also there in frequency domain specifications. So, out of this time domain transient part comes from the natural poles of the G of s, where the steady state part comes from forcing at plus or minus j omega. So here, when considering Laplace domain, we have zeta plus j omega, as I said before. So we are going to change, we are changing this from j omega zeta sigma plus j omega to j omega by forcing zeta sigma equal to 0, right? So the steady state response comes from the act of doing this, where the transient response part comes from the natural pole location of your g of j omega. So ultimately, your steady state part becomes a into some magnitude of the sine signal plus magnitude of g of j omega into sine of omega. So will be your final output response and considering this input response. Or I would not say this A. Maybe I will consider this as omega itself, right? Okay. Whatever part I consider here, it will come here. So this tells the nature of the system at each frequency you consider. So from ranging from 10 power 0 to 10 power something n infinity, I would say. Similarly, the frequency response of a closed loop system will look something like this. I would consider M of S, the closed loop transfer function, equal to G of S by 1 plus G of S into H of S. So here I am going to replace S with J omega, not sigma. Consider sigma to be 0. So M of J omega would be G of J omega divided by 1 plus G of J omega into H of J omega. Right? So the magnitude part become magnitude of M of J omega is equal to G of J omega mod modulus its absolute value 1 plus g of j omega into h of j omega, absolute value of this whole thing. So your phase becomes, this is magnitude, this phase, angle of m of j omega equal to angle of g of j omega minus angle of 1 plus g of j omega into h of j omega. Minus because this is 1. A by B can be written as angle of A minus angle of B. So why do we write like this is that it helps to analyze the stability and performance of the system directly from your frequency response. You don't need to calculate all this functions out of it. So writing your transfer function in terms of magnitude and angle will help you analyze the stability and performance. These are the two most biggest criteria in control systems, right? Whenever we design a controller, we used to see whether the system is stable. So ultimately, we want a stable system. We are not interested in unstable system. So even if the system is stable, we want it to behave in a particular way, desired performance. So stability and performance are the two eyes of the control systems, where we use some techniques and we make some trade-off between this. First criteria is to be stable, and in that criteria, how much best performance I would expect, I will tune my system according to that. This is the overall um, output expect from your control systems, right? So this magnitude and phase criterion will let you design your or let you analyze the stability and performance from this frequency response directly. And if I have in tricon and free time domains, I have different things like peak overshoot, peak time, rise time, peak time, some settling time, whatnot. These are all different things we have in time domain specifications or time domain responses. So for frequency domain, we have a similar thing where this we call it as resonant peak. And We call this as resonant frequency, where there it is time, here it is frequency. And we have bandwidth, where the frequency at which bandwidth is happening is this omega b, where your resonant peak mr, these are important formulas that we will use later. So this is the maximum value of your m of j omega, magnitude of m of j omega. That's the resonant peak at which the maximum value occurs in your frequency response. And the frequency at which this resonant peak occurs is the resonant frequency. And omega b is the bandwidth frequency, where this frequency corresponds to response goes to 3 decibels. In frequency response, often we define the system using decibel, dB. D is decibel. Okay. Instead of radians or any other frequency domain characteristics, we used to analyze things using decibels. It's a standard way to represent, because we 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 uh, we are sophisticated to use the log magnitude in frequencies than the normal plots or normal scale. And another frequency for this WB is the cutoff frequency, right? Both are same. Bandwidth frequency and cutoff frequency are same. For a second order system, in time domain, we have omega n square divided by s square plus 2 zeta omega n, s plus omega n square. So here we will have omega n square divided by s square plus 2 zeta omega n s plus omega n square. Oh, sorry, I'm writing the same way. Here it will be omega n square divided by omega n square minus omega square plus j 2 zeta omega n into omega. Maybe I will write it here. Minus omega. So omega square is a particular frequency at which we are examining, where omega n is the natural frequency of the system. So based on this, your MP overshoot formula here would be minus zeta pi divided by root of 1 minus zeta square. Here your resonant peak would be MR equal to 1 divided by 2 zeta root of 1 minus zeta square for all zeta less than 1 by root. The resonant peak occurs at resonant frequency that we have found using omega n square root of 2 zeta square. So bandwidth we will find using omega n root of 1 minus 2 zeta square. It's a little expanded formula, root of 4 zeta power 4 minus 4 zeta square plus 2. So you don't have to do all these things to find the bandwidth frequency. You can easily find it from the Bode magnitude plot or asymptotic plot, so that we will see. You don't have to panic about this. You don't need to memorize all these things. It's a standard formula, it tells on it. That's it. So in time domain, Ts depends on zeta omega n. In frequency domain, it also depends on zeta, but we will, based on zeta value, if it is low, it tells the resonant peak would be low. It is directly proportional. If zeta is good, your resonant peak would be good. Overshoot also depends on zeta. Here, resonant peak depends on the zeta. That's the difference. Okay, we'll solve one problem, basic problem on how to do this. S plus 1, and my input is R of t equal to sine of 10t. Find the C of t. How do you usually do for this system? Can we try using Laplace first? So in for Laplace, I would say RL I'm taking. I would give something like this U of t. So what we usually do in time domain, G of s we will write as it is 1 plus s C of s by R of s equal to G of s. So C of s equal to G of s into R of s, where G of s is 1 by s plus 1. U of t R of s would be 1 by s. So we will have 1 by s into s plus 1. A by s plus b by, we will do partial fraction since both are in cascade. A into s plus 1 plus bs equal to 1. Putting s equal to minus 1, I will get minus b equal to 1, b equal to minus 1. Putting s equal to 0, a equal to 1. Right? Now I will get 1 by s plus or minus 1 by s plus 1. So this 1 by s will be e power minus t. Oh, 1 by s will be 1 minus e power minus t. So this is your output response C of t in time domain. Now we are going to do the same using frequency domain. Can you do along with me? Only thing is u of t or your input becomes r of t is equal to sine 10t. That is a change because in frequency domain we would give input as a sine signal, right? And analyze the output based on that. So you here the input is sine 10t, C of s is same 1 by s plus 1. How do you do that? This is G of s, okay? So I want C of t, but using the frequency domain representations. All calculations should be done in frequency domain. So first, we will simply replace s is equal to j omega. G of j omega equal to 1 by j omega plus 1. So this is the first step, right? The next step is to find the magnitude g of j omega. Magnitude of g of j omega is 1 by j omega plus 1 magnitude. So how do you find magnitude for a complex representation of the system? Okay. How do you do that? 1 by a square plus b I, uh, 1 by a plus bi. How to represent this as a magnitude? Root of a square plus b square, right? So similarly here it will be 1 square plus j omega square, j square omega square, it will be 1 by root of, here omega is 10, 1 plus j omega, j square would be it will along with j it will be plus, otherwise it's minus. It will be 10 square divided by 1 by root of 101, right? This is the magnitude representation of a signal. Similarly, phase, how do you write? Numerator minus denominator. So numerator is 1 minus denominator would be minus of tan inverse of b by a, where b by a is 1 minus tan inverse of 10 by 1, where your a plus j I b, right? So this is 10, this is 1. So this is b by a, tan inverse of b by a. So 1 minus tan inverse of 10, the value would be around, how much it is, tan inverse of 10? be 84 degree around, something around 84 degree. It would be. So your output will be your magnitude. What is your magnitude? 1 by root of 101 to sine of actual 10t minus or plus. Oh, this is minus 84. So minus 84 degree. This is your pi. So when we compare this with the explanation given here, where is that part? You give a into sine omega t and you got b into sine omega t plus pi. For a into sine omega t is sine 10t. What we got is 1 by 1 root 101. This is b sine omega t as it is plus phi, where your phi is minus 84 degree. Clear? This is how we find the output responses in frequency domain.
Ma'am,
Mm.
that one is for that closed loop, right? 1 minus 10.
Which one? Here, this one.
The angle of
Yeah, it's for like numerator minus denominator. We used to take no angle of numerator minus angle of numerator angle is 1. So 1 minus angle of denominator here in angle of if I represent a plus bj complex number, it would be tan inverse of b by a. That's how we define for a complex number. So tan inverse of b is 10, a is 1.
but numerator is 0 now.
Angle of numerator, oh, for constant, yeah, then it would be a closed loop representation, right?
Yes.
Then we'll move to, I think I covered everything in first lectures. Frequency responses, closed loop system, yeah, this would be. And resonant peak done, frequency done, cutoff frequency done. And second order system representation is given. This we covered. This also we covered. Yeah, mostly everything is done. In lecture 2 is about the Nyquist plot. Okay, let me go through all this once. Stability, frequency, stability criterion, what the cover. Okay. So when you study stability in time domain, what you look for? How did we define a stability in time domain? We have split this S domain into RHS and LHS, and whatever that covers in LHS of the system, and if the poles lie in this direction, whatever way I have highlighted. So whenever the pole lies in this left half of the S plane, we define that as stable, and in right half of the S plane, we define this as unstable. So this practice we had in our time domain system where we chase the poles of the left half of the S plane. When you study stability in frequency domain, you track, instead of poles, you track how systems frequencies or frequency response, output response run around a specific point That is a magic point called minus 1 J 0. Here it is. So we would be interested in this point instead of origin. We would be interested in this point. This is distinctly because when you write a closed loop system, you would write like G of S divided by 1 plus G of S into H of S, right? So when comes stability, whenever we look for stability, we look for poles where the poles will be always located in the denominator of the system. From this denominator, we used to calculate the characteristic equations. How to use characteristic equation? This characteristic equation is the denominator equated to 0. So if you factorize this and find the factors, then you call that as a pole. Based on this pole location, you find the stability. Similarly, if you want to do the characteristic equation for this, I would equate this to 0. So when I equate this to 0, this will give me minus 1 plus J0 is just imaginary is 0. That's it. So we are looking for stability in frequency domain at this point, particularly at this minus 1 plus J0 point. Is there any doubt in this?
No.
Right. The first method we are going to see in frequency domain analysis is this Nyquist plot or the polar plot we used to call. Both are similar to each other. Where Nyquist plot is you drawing the complex numbers of the transfer function or the loop transfer function g of j omega into h of j omega as the frequency omega goes from 0 to infinity and back from minus infinity to 0. So it will be a complete loop of the your transfer function. In root locus, what we did is k of g of s, h of s you have. So this k, we vary from 0 to infinity and with varying k from 0 to infinity itself, we got the root locus symmetric. If it is like this, it will be symmetric around the real axis. Similarly, here we are going to change instead of k, we are going to change omega from 0 to infinity and look from infinity to 0. And how this plot varies, based on this we are going to fix on our stability and the performance, and we are going to carefully around this point minus 1 plus or minus j omega plus j omega. Okay. So this is going to be our goal in the Nyquist plot. So in Nyquist plot, how will we design the stability? That's the important point here. So think minus 1 as a center of attraction, and if the path loops around minus 1 in a certain way, the closed loop system becomes stable. How the certain way is defined as Z is equal to P plus N, where P is your open loop poles, N is the number of times your Nyquist plot encircles in counterclockwise. This is very important. This is counterclockwise or anti-clockwise used to say around minus 1 plus J0, where Z is the number of closed loop poles at right half of the plane. So just be careful with all this notation. Z equal to P plus N, where if I have an Nyquist plot like this is the minus 1 plus j omega region, and I am getting a Nyquist plot maybe like this. Okay, if this is my Nyquist plot, and I am putting a note direction with this, maybe it comes from infinity. It goes to infinity, it comes from infinity. So with this, Z is the number of closed loop pole at RHP, right half of the plane. N is the encirclement. P is the open loop poles at open loop poles of the system. N is the encirclement. So if I give G of S is equal to, I'm randomly giving, not connected to this Nyquist plot. So I'm giving S plus A. Oh, this also comes RH, right of plane. Okay. S plus B, S plus C, S minus D. So this is the G of S, H of S. How many number of open loop poles lies in the right half of the plane here? Poles are the denominator. So how many of this lies in the right half of the plane?
One.
One. One lies in the right half of the plane. One unstable pole is here. Right. With the figure, I have mentioned anti-clockwise direction. Anti-clockwise is this. Anti-clockwise direction. And how many curves are around this minus 1 plus j? How many times it encircles?
One time.
One time. So your P is equal to 1, N equal to 1. So when I add this together according to this formula P plus N, it gives me 2, where 2 is the number of closed loop poles RHP, where closed loop poles design the stability of the system. If two closed loop poles lies in the right half of the plane, what does it mean? Whether the system is stable or not?
No.
No stable. It's not stable system. So from this, we define the stability of the system. So do you remember any similar thing you did in time response analysis? How many number of poles in right of plane, left of plane? How did you do that analysis?
Routh.
Yeah, exactly. Routh-Hurwitz you did, right? So with Routh-Hurwitz in time domain, we did the same analysis. For frequency domain systems, for system represented in frequency domains, we use this Nyquist plot analysis to tell whether the closed loop system will be stable or not only with the open loop representation of the system. We don't need much information about your closed loop poles. We don't have to explicitly calculate everything about your closed loop system. Just from this open loop system, and if you do some calculations of Nyquist plot, if you do Nyquist of the system in MATLAB, it will give you all the details about your system. So this is the idea behind the Nyquist plot analysis.
Ma'am,
Yeah,
P is equal to 0 and N is equal to 0 for stable systems, is it?
we cannot tell like this. So when we can have something like this, no? That also will make close to pole zero.
So if it is clockwise, then we take it as negative, is it?
Yeah, then the formula will change. Just stick on to one formula. Many textbooks have different formulas. It would be something like n minus p equal to z when considering clockwise.
Okay, okay.
So stick on to one formula.
Oh, okay.
Just calculate anti-clockwise how many times it rotated it anti-clockwise. If it hasn't rotated it anti-clockwise, then it is zero.
Even if it rotates clockwise, we take it as 0.
Zero. Only this for this particular formula z is equal to p plus n. If you consider, it will be zero.
Okay.
And calculate your open loop poles, then you will get how many closed loop poles will be in the right of the S plane.
Okay. On what condition will N becomes negative? Huh?
N becomes negative.
Just now you wrote
Uh,
minus 2.
oh, okay. Arbitrarily I gave. Maybe no. Oh, okay. Then that way it won't be. I couldn't think of anything in particular. Yeah, we will solve some problems and see. I couldn't think of any example for that.
Yes, ma'am.
And if I come across the problem, I will let you know in this way too. Okay, detour around this triangular circle. Okay. We can take a general representation g of s into h of s equal to k by s into ts plus 1, where you have one pole at origin and another pole will have s is equal to minus 1 by t, right? And from this, there is no pole at right half of the plane. So P will be 0 in this case. So if I take the system like this, so I would first point how to write a Nyquist plot, or how to define it, that we want to see. So the g of j omega and h of j omega, the first step is to s is equal to j omega x. G of j omega, h of j omega would be k by j omega into t into j omega plus 1, right? So I want to write it in terms of magnitude and the phase. So for that, I would want to simplify this since it is in a complex domain representation. So I'm writing again in terms of g of j omega 1 plus t j omega. I'm multiplying this with 1 minus t j omega in numerator and denominator, t j omega. So this will give me k into 1 minus t j omega divided by j omega into 1 plus omega t the whole square, getting rid of the complex term in the denominator. And j omega can be there because it's a simple imaginary value. So then the g of j omega becomes k by j omega plus omega t the whole square minus j omega into kt divided by j omega into 1 plus omega t the whole square. So just split it, k into the thing I did in this step. So if I want to simplify each part, the first part, this one, this will become k by j omega will be minus j into k by omega. Can I write like that? So the next term k omega t by j omega minus j into some whatever terms we have here. This will be minus j into, I'm taking j to the numerator. Kt divided by omega will get cancelled. J will also get cancelled. No? J of kt by 1 plus omega t the whole square. Okay. You can cancel both of that. No? Only this term will come. This will give me k by omega minus j k by omega into 1 plus omega t the whole square plus kt by j and j will get cancelled. 1 plus omega t the whole square. Now, this is the first step. First step is to substitute. Step 1, what we did is substitute s is equal to j omega and simplify it. The step 2 is to examining the endpoints. So we are interested in changing the frequency omega from 0 to infinity and back from infinity to minus infinity to 0, right? So we want to evaluate at each point. First, we'll just check at the endpoints. So what if omega equal to 0 and what if omega equal to infinity? So we will do that analysis. When omega equal to 0 here in this equation, g of
There is one type of
where
1 plus omega t the whole square. It's the second term.
here
Kt by
omega is 1 plus omega t square,
yes.
right? Okay. So when omega goes to 0, here this omega, since it is in the denominator, it will make it infinity. So all this term g of j omega into h of j omega will be infinity because there is addition. So anyway, infinity plus anything infinity. So when omega equal to infinity, how this will be? It will be the opposite to that, right? G of j omega into h of j omega becomes 0. So as omega varies from 0 to infinity, your Nyquist plot will come from infinity to 0. Something like this it will come. Okay, we don't know at what pattern it will come. It can come like this or it can come like this. Not like this. From infinity it can come like this. So somehow it is going to reach from infinity to 0. Right, that we understood. The next step is to analyze, does it encircle minus 1? Because we are interested in stability, right? So we are going to see whether it encircle stability or not. So once we found from at what omega value how the transfer functions will look like, so from that you would be able to examine whether it encircles minus 1 or not. So based on this encirclement and the location of open loop zeros, open loop poles and the encirclements, you would be able to say whether the closed loop system will be stable or unstable, right? So that's how the whole this Nyquist plot we used to do will work. Now we'll solve one problem based on this. F is H of s equal to 10 by s into s plus 2, right? So solving s is equal to j omega, I will get 10 by j omega into j omega plus 2. So multiplying numerator and denominator, j minus j omega plus 2. Careful to use minus in the imaginary term. You cannot write j omega minus 2. Right. This will give me minus 10 j omega plus 20 divided by j omega into 4 plus or minus omega square. Right? A plus b into a minus b, a square minus b square. So it will be plus 10. Okay. Then this can be written as 20 by j omega into 4 plus omega square minus 10 j omega by 4 j omega into 4 plus omega square. So I have splitted that into two different parts. So if I want to simplify this, this will become 20 by j omega will come minus j 20 by omega. The second term 10 by 10 omega by j omega becomes minus j into 10 minus j it will be. So combined we get g of j omega equal to 20 by minus j 20 by omega into 4 plus omega square minus j 10 by 4 plus omega square into j. Right. Now, you want to see how the omega changes, how changing omega will change the Nyquist plot. When omega equal to 0, g of j omega becomes infinity because omega is there down. J won't come 0. So because of this omega, this will go to infinity. When omega equal to 0, again this will go to 0. So I'm to write this as infinity minus infinity. So at what direction it is coming, that we have to calculate, right? That angle we have to calculate. How to calculate the angle? This will become angle of 20. It will be 0. 0 minus j omega. For j omega, it will be just omega tan inverse of omega by 1. Tan inverse of omega minus tan inverse of omega by 4.
Ma'am, that minus 10 divided by that omega is not there, I think.
Omega will also go away, right? Yeah. So let me know if I do mistakes like this. So this will give me tan inverse of 0 minus tan inverse of omega by 4. So this and this will get cancelled. Only minus tan inverse of omega I have. Any mistakes I made here?
I mean, the last step, can you repeat, ma'am?
Just finding the angle for this transfer function. So here it will be 0. 1 minus j is there, no? It will be 90. It won't be 0. Right? For this j is above 90 minus this will be 0 anyway. Omega will be 0. This will be tan inverse of omega by 4. And here it is 0 because of constant. Here it is tan inverse of omega by 4. Any any mistakes I made here? It's right, right? So this will give me 90 minus tan inverse of omega.
Ma'am,
Ah,
in denominator we don't have j, ma'am.
yeah, it went to the numerator here.
Yes, ma'am. So that
Minus j.
minus, okay, ma'am.
Okay.
Oh, then this is just tan inverse. The whole thing will be tan inverse of 20 by omega 4 plus omega square divided by 10 by whatever.
See, I will write it separately.
Yes, ma'am.
So this will be minus 10 4 plus omega square. This is a constant term here. The j and j will get cancelled here. Omega will get cancelled.
Yes, ma'am.
Uh, j omega cancel. So remaining I have this. The next term is this term with the j. The j I brought it up like to the numerator for simplifying the terms. So it will be 4 plus omega square, right? So now if I calculate this for 10 minus 10 will be 0. Numerator there is a only constant term 0 degree minus of
No, ma'am. Ma'am,
denominator.
this is in a plus jb form, no, ma'am.
Yeah.
So we can directly write it as tan inverse of b by a.
Yeah.
So
Since
we
it
don't.
is in the denominator, it will be minus, no?
There is no j term in denominator.
Okay, then we can write it from this. Instead of taking a simplified terms, we can write it from this. It will be easy. Okay. So that is for magnitude calculation. 10 j omega divided by j omega plus 2, right? So how will you write angle for this? For angle 10 will be 0. For angle of j omega,
Yes,
it
ma'am.
will be 90 degree.
Yes, ma'am. Minus
I'm
90.
just writing for j omega, 90 degree. We will
Yes.
come for the denominator part.
Yes, ma'am.
Angle of j omega plus 2 will give me tan inverse of
Omega b.
omega by 2.
Yes,
Right.
ma'am.
Now if I write angle of 0 minus everything this here in the denominator, right? So it will be 90 minus tan omega inverse by 2.
Yes, ma'am.
Right. So this is our angle. So here, the part here is 1 by 2, it's not coming. That's a mistake we did. And this is my 90, that this minus will come here. That is correct. But this mistake we did somewhere. So that we have to check. Okay. Now we found the angle. Now with this angle, we will calculate when omega equal to 0, how this angle will be. 90 minus tan inverse of 0, 0. It will be 90.
Yes, ma'am.
Uh, Let me check once. Tan of 0 is 0. Tan inverse of 0 will be 1 infinity, I think. 1 by 0, no? So it will be infinity. So when omega equal to infinity, this will give me, again I need this, right? Minus 90. Okay. Minus is common. So it will be minus 90. Anyway, it is infinity. So here it is minus 90 minus tan inverse of infinity. This will give me minus 90 only. So from here, the Nyquist plot, if I take 0 minus 90 minus 270, sorry, 180 minus 270. Otherwise, it may also be 90, 180, 270. But we are going to follow only anti-clockwise directions. I'm just taking the first one. This minus 90, minus 180, minus 270. If we see, it comes from infinity when 0, omega equal to 0. Inverse. Tan inverse of 0 also 0. So we are making very no mistakes. Okay, this will be 90. Yeah. So it comes from minus 90 to minus 90. So if I take this category, blue rounded thing, so 90 would be this direction. So it comes from here to here, straight. It will be minus 90, 90 to minus 90 it is coming. From this, we found in the magnitude it is coming from infinity to 0. So minus 90, it comes from 90 at infinity and goes to 0. So your plot would look like this. So magnitude will comes from infinity to 0. Your angle comes from 90 to minus 90. So it will be like this. Your Nyquist plot would look like this. Right? So everything is in this quadrant. So nothing, there is nothing that encircles minus 1 here, minus 1 here, that nothing that will encircle minus 1. So your n would be 0, your p is equal to also 0. That's why your z will be 0. So z is equal to n plus p, z will also be 0. Your closed loop system will be stable. So this system 10 by s plus 2, s into s plus 2 is closed loop stable. Right?
Okay.
Okay. I will ask a few basic questions like practice questions in week 7. This Nyquist plot based on this. Week 7, right? G of s h of s equal to s plus 2 by s square minus 1. Can we solve this? Can you try solving it? I will solve with you. So your g of j omega, h of j omega would be j omega plus 2 divided by j omega the whole square minus 1. So this will itself give me, I don't need to calculate it, minus omega square. It will automatically give me. So if I want to find the magnitude, uh, g of j omega, h of j omega, this will give me root of 4 plus omega square divided by minus 1 minus omega square. When omega tends to 0, this gh will be root 4 equal to 2 divided by minus 1. This will be minus 2. Right, like when omega tends to infinity, this will be g of jh will become infinity. Infinity by infinity, we cannot say anything. Just infinity it is. So if I find angle GH, how the angle would look like tan inverse of omega by 2 minus 0. There is nothing, J is not there. Minus 2 tan, how it will be?
Modulus means sign will not be there now.
Absolute value of this, yeah. Right, right. So it will be omega, it will be 90. For omega square, it will be minus 180. Right? So your magnitude will be 2 to infinity. Oh, sorry. For this, we have to find, right? When omega equal to 0, 0 to minus 180 degree. And omega equal to infinity, it will be 10 to infinity is also 0. So it will also be minus 180, right?
Ma'am, how do you write minus 180, ma'am?
It's for omega square in the denominator.
Okay.
One minute. It's for s plus 2. You'll plot in MATLAB and we'll say. Yeah. So, and that was meaning in the class. Okay, back to this. So it is minus 180 to minus 180, right? Now, uh, omega equal to 0, it will be minus 180. By 2, it will also be by 2. So 2 omega by 2 it is. If omega is equal to 0, it will be 0. Infinity, it will also be infinity. Okay, instead of doing this, like in constant, in denominator is a constant, we will calculate both at my 0 and infinity. So if you see, this would be minus 2 plus j omega, right? So somewhere in j omega, maybe here or here, based on the omega's values, it will change. So since it is located in the real axis this side, when comparing the omega equal to 0, this will be minus 2 only, plus j 0, right? So it will be negative real axis, it will be minus 180 degree. So when compared omega equal to infinity, this will be infinity. So this will go to the value that is infinite. So this will become infinity like here. If this is 180, this would be minus 90 degree. I don't understand why this will be like this. I'm checking whether I have written the correct answers or not. This will become zero anyway. This can be written as 2 plus j omega divided by 1 plus omega square. That's how we wrote minus of. So this will can be written as plus j. uh, and if I take omega commonly out, this will become omega plus 1 by omega. In order to take all these things, we can straight away write it will be only minus j it will be. So it will be infinity j omega by omega square. Omega should be 1 by omega into j. Infinity becomes 0 and in terms. Sorry for the confusion. Let me just rewrite it and write it in the step. G of s, h of s equal to s plus 2 by s square minus 1, right? So when I write it in terms of g of j omega plus 2 divided by j omega square minus 1. So this will give me 2 plus j omega divided by minus 1 minus, this will become minus 1 minus omega square, right? So far it is okay. So we want to check both the g of gh magnitude and the direction here, right? When finding the magnitude g of j omega into h of j omega, this will become 2 plus j omega divided by minus 1 minus omega square, absolute value. If I find this, be root of 4 plus omega square divided by, this will be same 1 plus omega square it will be. Okay. So at omega equal to 0, when omega tends to 0, this will become 2 minus 2, but absolute value become 2. So g of gh will become 2. So if I check the angle here for the same, when for angle we will take the sign, right? Not absolute value. When you check the absolute value, this will become instead of here substitute omega equal to 0. So it will give minus 2 plus j 0 because omega equal to 0. So this will give me, it lies in the negative real axis. So the angle becomes angle of g of j omega into h of j omega will give me minus 180 degree when omega equal to 0. Similarly, when omega equal to infinity, if we check here, if I substitute infinity, my for magnitude, j omega by 1 minus of 1 plus omega square, right? If I substitute infinity, this 2 will go. So I will get j omega divided by omega square. Minus 1 will also go. So this will give me j by omega. So this will be minus 1 by omega into j. So if I substitute infinity here, magnitude would be magnitude of j omega into h of j omega would be 0 because 1 by infinity equal to 0. If I check angle, omega would be infinity. Anyway, the magnitude corresponds to 0. It doesn't add much value. So it will be approximated as minus j. So minus j, if I take tan inverse of minus j, it would be minus 90. So when omega equal to infinity, your angle would be GH would be minus 90. So omega equal to 0, omega equal to infinity. Your magnitude will be 2, 0, angle would be minus 180 to minus 90, right? So if your Nyquist plot for omega equal to 0, it starts with 2 at minus 180. So 270. So at minus 182, it is starting. And when omega goes to infinity, it will reach, what happened? It reaches 0 at minus 90. So your plot would go like this. This would be your direction. Since this is 2, it would be symmetrical about if I find c e power minus j. Here somewhere your 1 would be. So it is circulating your 1 times clockwise. Huh? So how will you say the stability of a system?
Ma'am, minus 90 will be below, no, ma'am.
No, I'm taking anti-clockwise direction. Otherwise, it would be minus 90 would be below. Okay, right, right. If I take this 90, 180, no, it's correct. Minus 90 would be above only. Otherwise, it would be like this 90, 180, 270. It's correct, no? This is a negative direction minus 180 for this to be 0.
Okay.
So your Nyquist would look like something like this. It is circulating your minus 1 by clockwise direction once. Right? So your n would become p would be here from poles how it is s square minus 1 plus s plus 1 into s minus 1. So one pole is in RHS and your anti-clockwise direction is 0. So one will be in the closed loop poles. So your closed loop pole will become unstable. Your system will be naturally unstable. I will give you one problem from book Norman and Nice. You can solve that. present my screen from my laptop. So we'll try to plot this in our MATLAB and see how it is rotating and what we can infer from this. I hope you can see my laptop screen, right? MATLAB. This is k by s into s plus 3 by into s plus 4. So g1 would be transfer function is equal to df of s. So g1 would be k. I will just give k equal to 1 first. G1 is equal to k divided by s into s plus 3 into s plus 5. It's open loop stable. No poles are in the right half of the S plane. So it is open loop stable. S into s plus 3 into s plus 5. So we will calculate it by hand and also by this. The MATLAB keyword for Nyquist is G1. See, sorry, Nyquist. This is the keyword for the Nyquist to plot the Nyquist. As we did for root locus, it is R locus, right? Similarly, for Nyquist, it is Nyquist, same word. We will plot both Nyquist and root locus. This figure will create an environment for this. If you plot only one figure, you don't need this. If you plot multiple figures, you would need this to separate those. So this is your root locus plot and this is your Nyquist diagram. Where if you see closely, so this is the direction. It goes from minus 270 to minus 90. And it is not crossing minus 1. As you see, it is minus 0.08 only the left hand side is. So when you see this is an open loop 0. It is circulating here, but not around minus 1. This is circulating somewhere before that. That's what we are seeing here in MATLAB also. This is how you can compare the hand-drawn diagram with the MATLAB diagram. So just check the real axis values and you can see it is not crossing the minus 1. And in Nyquist in MATLAB plot, you will get this direction also. So it is actually rotating in clockwise direction, right? So it is rotating in clockwise direction here also. It's a complete plot. We are just interested in left hand side. So we are seeing this left hand side. You can plot both side also. but it is going to infinity, so you cannot see that here in this plot. That's why actually it is circulating. This is a complete plot, you cannot see that in MATLAB. That's it, but don't get confused. Okay, we'll do this part. Okay, now since we have open loop zeros, no open loop zeros, your p would be 0, and there is no encirclement also, so your closed loop system would be stable. It's supposed to be stable, right? So you'll check whether it is stable or. So I'm considering unity feedback. How to write a closed loop system? Feedback of G1, comma 1. So this will consider a unity negative feedback and write the closed loop transfer function. I will show the open loop and closed loop transfer functions. So this is G1, C11 is the closed loop transfer function. Here if you see, so this is 1 by s cube plus 8s square plus 15s, right? Here it is s cube plus 8s square plus 15s plus 1. It is added, it's a closed loop transfer function. Since I consider k equal to 1 and there is no 0 above, right? Now it will be, I'm going to see the poles of closed loop 1 and the closed loop poles. I will just type it here. It will be pole then. Ah, see, everything is in negative. So the closed loop system is stable from the calculation we did. So we'll check if for one example that is unstable, open loop unstable, but closed loop stable. Couldn't say something. Maybe in problems we'll see. Mm. Here, magnetic blocks. There is any examples that has open loop poles. Square plus 4s plus 50. What will be roots of square plus 4s plus 50? It's also stable. Okay, let me just calculate from here. If we make this -1, -3, we'll see how this looks like. If it is -3 also, this becomes 0, 0.03. It's later. Yeah, so it comes through the root locus. See, we don't need 0.3 also. -0.3 would work. So I have a open loop 0 in the right half of the S plane, S equal to 0.3 I have taken. So here it is -1 is here. So -1 is here and it is rotating this in a Actually, it is not rotating. Huh? Clockwise again, it is rotating. It will be again. It is not actually. 0.9. Just trying to take an example where there is a open loop 0 in the right half of the plane and the system becomes closed loop stable. I'm not getting it. Fine. Here it will come. I'll keep monitor itself. Okay. Actually, it is not rotating. It is going around it, but it is not rotating. So consider this as a 0. Rotating the poles around the anti-clockwise direction will be 0. But I have an open loop pole at minus 0.3 or plus 0.3 RHP. So if we check the closed loop pole, it will be C positive. So according to our formula, Z is equal to N plus N, right? N plus P, where P is 1, N is 0. So Z will be 1. But here why it is 2? One pole is there. It is not rotating around it, right? So it might not be the valid diagram. Okay. I am trying to prove like with open loop unstable, closed loop stable, but I couldn't get any examples for that, even from this book. Okay, that's it. I will look for some example in some other books and I can show it in the next lecture.
Okay, ma'am.
We can solve few more problems and we will start with Bode next week and we can solve few more problems in Bode and Nyquist by Friday. For the next Wednesday, we will start Bode because the quiz is coming on November 23rd, right? So before that, we have to finish till week 8. I want to finish little early so that we can revisit 5th to 8th before the quiz. So last time someone have asked for some extra class. I guess that won't work that way. You can join live sessions and ask your doubts or whatever questions you have while solving a practice assignment or a graded assignment. It would be helpful. And I guess your week 8 and week 9 would be handwritten copies. It won't be like a MCQs as you do in your assignments. So you have to spare more time on that. So plan accordingly. Okay, thank you. If you have any doubts, you can ask. Otherwise, we can wind up
Um,
this.
week 6, the graded problem 5, if you can solve sometime.
Week 6 grade assignment. Problem 5.
Yes, ma'am. If one zero is added,
Addition of -1. Okay. It's for common question or week 6
yeah, it's a group question. I mean,
comprehension, right?
yeah, it's a part of a bunch of questions.
Okay. Yeah. From Q2 to 7, same questions, right? So
Yes.
the system is G of S equal to 1 by S plus 3. Oh, I'm not presenting it. Question is 1 by S plus 3 into S plus 5 into S plus 7 with the characteristic equation 1 plus kg of S equal to 0. Which of the points are in the root locus of the system? Okay. So when you write it in terms of 1 plus k into y plus 3 into s plus 5 into s plus 7 equal to 0. This will go there. Plus k will come, right? Just plus k will be added here.
The
Chapter.
fifth question is about if a zero is added, will system be stable for all values of k? It can't be stable for all values of k, no, ma'am.
With the addition of 0 at s is equal to -1. So it will be s plus 1 in the numerator, right? So there will be s plus 1 here.
Yes, ma'am.
Following system is stable for all values of k. So how will you find the stability in root locus? It will be based on that.
The route, no, ma'am.
Using route also you can say, yeah, if you do route Hurwitz, it will be s plus 1 into s plus 3 into s plus 5 into s plus 7. So this becomes s plus 3 into s plus 5 into s plus 7 into plus s plus 1 equal to 0. Some k will come here.
Yes, ma'am.
So s square plus 8s plus 15 s plus 7 plus k into s plus 1 equal to 0. Q plus square plus 15s plus 7 square plus 6s plus 0 is Q plus 15 square plus 11 51 is plus 105 equal to 0 plus ks
Okay.
plus 5. So SQ plus 15 is square plus 71 plus k into s plus 106 equal to 0. So this will become SQ, s square, s power 1, s power 0, 1,
106, 105 plus k, no, ma'am.
105 plus k. So 15, 105 plus k, 105 plus k minus 10 into 71 k divided by
So that minus will come the other way.
here it will come.
Oh,
No, it will be like this, no? Minus this. So 15 into 71 plus k minus
Minus.
105 plus k.
Yes.
Oh, here I have written. Okay, let us keep like that. 15 into 70. 15 into 71 minus 105 plus 16k by 15 minus 105 plus 16k by 50. So this will be 0. It's little larger. 2 divided by the whole time, so it will be just this. So either the k should be lesser than 105. No, no. K should be anything, right? K should be just greater than 0. K minus 105. This is for the first condition. Second condition, 10 into 71 and 0.65 plus 105. It will be some negative number plus 105. 0.65 minus
No, some number, ma'am. So that means that it
minus
can't be.
960.
So we
No,
can't say that it will be for all values of k.
mm, cannot because we have find a finite number, right?
Yes, ma'am.
The correct answer is given as true.
Yes, ma'am. Correct answer is or for all values of k, the system is stable. So I was
K will
thinking
be changed from 0 to infinity, right? Oh, that too, it should be greater than, or if it is less than 60, it is not stable.
something like that. Yes. So this is the right way, no, ma'am. I don't care about the answer, but what the way you have solved it is.
So, it's right, but he see it is minus 960, around 60 something. Okay, it may be
Hmm.
wrong. Okay,
Yeah, yeah.
minus 60. From this condition, we got k should be greater than minus 105 at least. From this
Okay.
condition, we got k should be greater than 60. Out of this, the closer value we have to take is k should be at least greater than minus 60, right?
Yes,
So
ma'am.
when drawing the root locus, the question is about root locus. It's not like common stability. It's under the root locus question. So in root locus, you are supposed to solve using root locus. Think in terms of root locus. In root locus, you draw a diagram of root locus by varying k from 0 to infinity. So the minimum value is minus 60. It doesn't bother when you change from 0 to infinity, right? So for all values of this will be stable because the minimum criteria is k equal to minus 60 from route you found. For all value greater than at least for all minus 59 up to minus 10 up to infinity, it will be stable. We are going to check for this value only, right?
Oh, okay.
So it will be stable for all value. It is true only.
Okay. So we have to bother about 0 to infinity.
For root locus. Because in root locus, you won't change k to minus infinity to 0.
Yes, ma'am.
So that's it. Okay. If you have any other doubts, you can ask. Otherwise, can wind up the session.
That's it, ma'am. Thank you, ma'am.
Thank you.